All right, welcome everybody. So this is, I believe, 66th Flow Talk, where Flow stands for Federated Learning One More Seminar. And it was created as a global seminar to provide a global forum for the dissemination of the latest scientific research results in all aspects of federated learning, including but not limited to distributed optimizations, learning algorithms, privacy, cryptography, personalization, and many more. Today, it's my great pleasure to introduce you our speaker, Christos, who is a machine learning researcher at Qualcomm and has been working on federated learning topics for the past couple of years. And prior to that, he received a PhD in machine learning from the University of Amsterdam under supervision of Professor Max Welling, working on topics involving Bayesian inference, uncertainty estimation, and compression for deep learning. And his current research interests lie at the intersection of federated learning with statistics, computation, compression, and privacy. And today, his talk is titled Tackling Computation, Communication, and Privacy in Federated Learning. Yes, thank you a lot, Christos, for accepting to give a talk. And please, one more thing. So for questions, so either please raise your hand, and this option is available in participants menu, or just post your question to chat. And after that, I'll try to unmute you so we can have a bit of an interaction with the speaker. Yeah, with that, thank you again, Christos. Please go ahead.
Yeah, thanks, Samuel, for the nice introduction. So I'm going to talk about computation, communication, and privacy in federated learning and how we can design sort of methods to tackle these two parts. In Qualcomm, we're sort of interested in 4 key challenges in federated learning. The first one is the statistical challenges that arise due to the fact that each user has its own data generating mechanism and thus leads to non-ID data. And parameter averaging in this case can be suboptimal and destroy progress. We are interested in security and privacy sort of concerns, since model updates can still leak information about the user data, even though we do not transmit the data themselves directly. And as a result, we also need to be robust to malicious participants in the federation. Communication is also one other important challenge, since in federated training, we need to communicate potentially large models between the server and the user. And this can quickly become expensive. And sometimes the cumulative communication cost can be significantly larger than actually just sending the data over. And finally, federated learning requires on-device training and computation. So we also need to adhere to the limited hardware capabilities and be as efficient as possible. So the agenda for today's talk, we will talk about 2 things. The first part is how we can do federated learning through graphical models. Essentially, we'll show how we can formalize federated averaging as a specific form of learning in a graphical model. And then we will show how we can extend it to FedSparse, which can allow for more efficient computation and communication. In the second part of this talk, we will talk about how to realize private and communication efficient federated learning. And we will show how privacy and communication sort of costs are 2 important bottlenecks, and how with one method we can tackle both at the same time. Right, and without further ado, let's go to the first part, where I will discuss how I can do federated learning through the lens of graphical models. So the main motivation behind this work is primarily to understand and be able to extend federated learning and federated averaging, since on first sight the algorithmic choice can seem a bit peculiar. Why averaging the parameters makes sense. And furthermore, practical applications of federated learning, as we discussed, have several challenges that need to be addressed. We want efficient models for on-device training in order to reduce the power consumption. We also want to reduce communication costs, since download and upload might then be a challenge that are not free. And there, of course, there are many others. So then we sought to formalize the federated learning framework and allow for easy extensions to address some of these issues. All right, so we will start by considering a simple hierarchical model over S clients. Each client will have some latent parameters, phi of S, which can be understood as the parameters that are used to make predictions on the local data set, D of S, and could be the parameters of a neural network in this specific example. Now, instead of directly optimizing these local parameters on their respective datasets, we would like to share some information between the users. And this is primarily since we assume that the users themselves do not have enough data to learn a good model on their own. So how to realize this information sharing? We do this via introducing a prior distribution over these latent parameters phi of s, which is parameterized by W, and W is sort of given by the server. And the hope is that W will learn to capture the common information across all clients and can be seen as the global model in the federated learning nomenclature. Right, so more formally, this corresponds to assuming a specific marginal likelihood on its client, where the probability of a client-specific dataset D of S depends on the server parameters W, and this is obtained by sort of marginalizing away the local latent parameters phi of S. And then the whole federated training is to find a way to optimize this specific global model, and how we can do that is by just trying to find the parameters that maximize the sum of marginal likelihoods across all clients. Right, and a traditional way to obtain this W star is to use the expectation-maximization algorithm. So the EM algorithm has two stages, as the name implies, the E step and the M step. In the E step, what we do is we compute the posterior of the latent variables phi of S, conditioned on the local data set and the server parameters W, and this can be done independently for each client. And then as soon as we do that, then we have the M step, where what we do is we maximize the expected under the posteriors we computed in the E step, joint likelihood with respect to the global parameters, server parameters W. And due to the specific form of this graphical model, it suffices to essentially find a W that maximizes the cross entropy between the local posterior distributions and the server prior. All right, so it turns out that this specific expectation maximization procedure can also be seen as doing coordinate ascent on what is called the evidence lower bound of the hierarchical model. So how this evidence lower bound arises is by assuming that we have a specific approximation to the true posterior distribution that we want to compute in the E step. And that approximation we dename as Q and has some learnable parameters nu of S. And then for this specific graphical model, we end up with an elbow that looks a lot like this, where I don't know if you can see my mouse, but we have an expectation over Q for our local approximation of the log likelihood of the data. And then two terms that sort of encourage the approximate variational approximation to be close to the server prior and also have a relatively high entropy. Now, it turns out that if we keep W fixed in this specific expression and we optimize the new 1 to S for its one for its client, we will actually recover the true posterior in Q. That is, of course, assuming that our approximation is flexible enough to support it. So therefore, this will correspond to the E step. And then what we can do is we can just freeze these parameters V and just optimize W in this specific expression, and in this case, we will recover the M step. So essentially, the evidence lower bound is called a lower bound because it is a lower bound to the true marginal likelihood, and the gap essentially between those two is the KL divergence between our approximate posterior distribution Q and the true posterior distribution P. So if we can do the E step exactly, then it's the same as maximizing the marginal likelihood. All right. So the problem is that in many models of interests, in the federated settings, such as neural nets, the C step is intractable. And what we can do is essentially throw away all of the inference and do something much simpler, which is the hard EM algorithm. So instead of doing inference in the E step, we will perform another simple maximization to find the most probable point of the posterior. And this we call the hard E step. And this will give us several parameters, one for each client, phi star of S. And then the M step simply becomes the task of finding the server parameters W that sort of maximize the probability under the prior of each of these client-specific points. Now we can still formalize this in the elbow sort of formulation by just assuming that the approximate posterior distribution Q is sort of a delta peak centered around the value of the parameters nu of S. All right, and then tying everything together, what does all of this have to do with federated averaging? So we can consider that the sort of server prior is a simple Gaussian prior centered at the server parameters W. And then if we write out the elbow formulation of EM with a delta sort of approximate posterior, we end up with an expression which involves finding the local parameters that maximize the local likelihood, and then trying to keep the local parameters as close as possible, subject to a parameter lambda, to the server parameters W plus some constant C. And then instead of fully optimizing the new parameters to convergence, we will only optimize them for a fixed number of iterations, while again keeping W fixed. And this will now give us the new prime of S. And then we see that if we compute the M step, given this new prime of S, we first see that the gradient is essentially the sum of the sort of local weights versus difference of local weights with respect to the server weights. And if we set that to 0, we see that the stationary point is just the average of the client specific parameters for the global model. And essentially, this now corresponds to the federated averaging procedure, since we can take the limit of lambda going to 0, because the federated averaging procedure doesn't really do any regularization of the client level, and we end up with a scheme that is federated averaging. All right. So, what are the benefits of this view? Well, first of all, we ground federated averaging as a specific form of learning in a given graphical model. It sort of connects several recent works in federated learning. For example, the difference between the local and the global parameters has been used quite often as a pseudo gradient to optimize the server parameters. And we saw that through this view, it is actually just a single gradient step for the M step, instead of doing a closed form solution. If we use a non-trivial lambda, we recover FedREC algorithm, for example. And furthermore, it connects federated learning and federated averaging to meta-learning, as the graphical model we start with is common probabilistic meta-learning. And if we actually do a gradient-based update for the M step in this specific model, what we get back is the reptile meta-learning algorithm, another algorithm that has close ties with federated averaging. And besides that, it also allows for several straightforward extensions, which was one of the goals we discussed in the beginning. Since now we can use different inference algorithms for the inner loop. For example, the client can do Markov chain Monte Carlo or some kind of message passing procedure to obtain an actual proper distribution Q. And we can also have different server update behaviors if we just change the prior. For example, if we use a Laplace prior, the server, we essentially select the median instead of computing the mean of the client parameters. If we have a mixture of Gaussians prior, we will perform clustering at the server, so we'll end up with K models instead of only one. And there are many others. And now that brings us to FedSparse, which is one extension through the lens of the aforementioned framework, which attempts to do sparsity in federated learning. So one of the primary goals was to tackle practical challenges that arise in federated learning. So pruning is a way to tackle some of these practical challenges. Since pruning can reduce both communication, we only communicate a subset of the model, which is cheaper than sending the entire model. And it also reduces computation at the edge, since if we do pruning at the server, the edge device only has to train that specific subset that survived. Now, how we can do pruning in the federated setting? Well, this novel view makes it straightforward. We just change the Gaussian prior to a sparsity-inducing prior in the hierarchical model. Now, the prior we will use is called the spike and slab prior. It's the golden standard for sparsity in the Bayesian stats literature. We assume that there is some prior over a binary variable z, which we also call the gate, with some parameter theta, So essentially, theta denotes how probable it is for a specific parameter to be included at the model. And then whenever the state of that binary variable is 0, we sort of remove that local parameter entirely. And whenever the state of that variable is 1, we sort of have the Gaussian prior that we had before. And now how to optimize this model? Essentially, we need to learn the parameters W at the server and also the probabilities theta that are also part of the server. So what we do is, similar to federated averaging, we set up an elbow to get point estimates for these parameters. So to do that, we need to introduce some more distributions, approximate distributions, variational distributions. We have a approximate distribution locally for the gates, the Z's, for its client, where the U of S is essentially learnable. Its client can determine whether to keep or remove a specific parameter. For the distribution, approximate distribution over the neural network weights, again, we will do what we did before and have a delta peak at the parameters to be optimized. And whenever the state is 0, we'll just also assume that the client distribution sets the weights to be 0. Now, if we write out the elbow to be maximized, then we end up with a sum of terms, one for its client. And basically, the first term is something that looks a lot like a federated averaging objective with two main differences. The first one is we optimize the expected log likelihood under these gates, where essentially the specific sample for these gates turns on or off specific parameters. And now also the L2 penalty between the local parameters and the global parameters is weighted by the probability of the client keeping a specific parameter, which sort of makes sense. And then there is this other term here, LU, where the first part can be understood as a stochastic L0 penalty. So essentially it penalizes the probability of a client activating that specific gate. And if that gate goes to 0, if that probability goes to 0, then the client will have essentially pruned away that parameter. And then the second term is a cross entropy between the local client probabilities and the global server probabilities. Essentially prevents them from drifting too far from each other, and will encourage some.
Yeah.
Yes.
There is a question in audience by Sergey. Let me try this clarification question. I'll try to unmute Sergey.
Mm-hmm.
Sorry, what is this means? Circle with point inside it.
Excuse me, I couldn't really follow.
There's a formula. There's a formula. There's some operation.
Yeah,
v,
this one.
Yes, this one. V and some circle. Yeah, point.
Oh, that's that's element-wise product. So essentially, we multiply the parameters with either 0 or 1.
Thank you.
Yeah, so 0 will remove it, 1 will keep it as is. Yeah.
Thank you.
Yeah. Yeah. All right. Any other questions?
No, not at this moment.
All right. Good. Okay. And yeah, there is the this drift. Essentially, we require some sort of alignment that the client-specific probabilities will sort of look a lot like the server-side probabilities. All right. So as we said, its client optimizes an L0 regularized loss with respect to these two sets of parameters, U and U. And now, given that these are updated, we get U prime and V prime. And similarly, what we did before, we can either compute a gradient to update the server parameters W and server probabilities theta, or just find the stationary point. The gradient is basically we just weigh the difference between the local and the global model with a client-specific probability. And the stationary point, just a weighted average, where the weight depends whether a client chose to maintain a specific parameter. And yeah, similarly for the gradient of the server parameters, is sort of the ratio between the probabilities of keeping or removing a specific parameter between the local and the global. sort of probabilities, and the stationary point is just the average of the client-specific probabilities. So essentially, we see that the gradients and averages are simple and easy. All right. So how can we use this now to reduce the communication costs? So there are two ways. We can reduce both the server to client and the client to server communication. For the server to client, what we can do is prune the model before we communicate it. And this is easy because we don't really need any data at the server. We have access to this probability theta. So therefore, whenever that theta becomes smaller than a user-defined threshold, then we can just completely remove that specific subset of parameters. And in doing that, we also reduce the computational cost for the client, since from that point onwards, the clients don't really have to train that specific set of parameters. And now reducing the client to server communication. So what we can do, instead of communicating the actual approximate distributions that the clients train, we can just communicate a sparse version of them. So what we do is we set up a message R of S, which is the element-wise product of of a random sample of the gates Z of S and the parameters nu of S. And then we only communicate the non-zero elements of RS along with the state Z of S, which is binary. Now, in this specific case, we can still express the gradient and stationary points in terms of the non-zero elements of V of S and the specific gates Z. And overall, both of these approaches will lead to significant savings, especially when the global model becomes sparse. All right, and that's basically it. And now moving on to the evaluation procedure. We had 3 tasks: CIFAR 10, CIFAR 100, and FEMNIST. All of them non-IID splits. We used the LeNet 5 model for CIFAR 10 and FEMNIST, and a ResNet 20 model for CIFAR 100. For baselines and methods, we have federated averaging, of course, where we don't do any compression. We have federated dropout, where what happens is that the server communicates to its client a random subset of the global model, and then training and updating on that client only happens a specific subset. So it is related to FedSparse in a sense that FedSparse tries to learn what is the proper subset to send. And since FedSparse does a zero regularization of the client, one more obvious baseline is to, instead of doing L0 regularization, do L1 regularization at the client level to sort of learn a sparse local model. So that is our proposed FedL1 baseline. And for FedSparse, we have 3 variants that target either low, medium, or high sparsity levels to essentially get different points in the accuracy versus communication efficiency plots. So for evaluation, we measure global and local accuracy, both against the cumulative cost of communication. The global accuracy is the accuracy of the server model, sort of using the prior as for prediction, and it simulates the zero-shot performance on hypothetical new clients that might not have any data to fine-tune the server model on. And the local accuracy is the average accuracy of the client-specific fine-tuned models. You can think of them as the local posteriors on their client-specific test sets, and this simulates personalized model performance. So for that personalized model, we just keep the model that the client last communicated to the server. All right, so looking at the results for the global model accuracy. So on all tasks, we can roughly see that if there is a specific performance or accuracy that all of the methods can achieve, then we can get from 20 to 40% reduction in total communication. So that is both uplink and downlink with FedSparse. And the main difference is that on CIFAR 100, we see that in general, the FedSparse variants cannot really get as good of performance as federated averaging, although we do have essentially the low sparsity version of FedSparse practically reaches the same performance as federated averaging, but there is not that much essentially gains in terms of communication. Now moving on to the local model accuracy, again, sort of similar patterns. We we can see that we get comparable performance with 20 to 40% reduction in communication. We also see that FedSparse is better in general compared to federated dropout, except in the case of CFAR 100, where again, I mean, if we compare against the low sparsity, FedSparse is better than federated dropout, but if we compare to something that has more sparsity, federated dropout tends to do a bit better. All right, and yeah, I argued about sparsity. So what kind of sparsity levels do we get? This also shows, serves as a proxy to how much computation we also save. We see that basically we can get up to 60% model sparsity if we adopt the FedSparse high sparsity sort of setting. And also interestingly, the sparsity levels are achieved quite early in training. So therefore, for most of the training, there is not really any sparsity, any extra sparsity, and the model is just trained on this specific subset that was identified early in training. So therefore, that's where primarily most of our communication gains arise. In contrast, the FedWell1 baseline that we had, it takes much longer to converge to the sparse model, and that's why it didn't perform as well in our experiments. All right, and this brings us to the conclusion for this first part. We introduced a unified view of federated learning through the lens of relatively simple graphical models. In doing that, we bridged several recent works on FL. We connected federated averaging to meta learning, and we provide a good basis for future extensions. One of these extensions we proposed ourselves, that was the FedSparse, where we learn sparse models in the federated scenario to reduce both communication and computational costs. And depending on the task, we can get specific accuracy with up to 40% less communication and 60% model sparsity. And as for future work, we'd like to move beyond getting point estimates for the local parameters and do proper inference, be it variational inference or Markov chain Monte Carlo. And this will be useful in obtaining model uncertainty in the federated setting, which is important for safety critical applications of FL. Yeah, so now going to the second part. So if there are any other questions for the first part, that would be a good time to ask them.
So please, as a reminder, just pause your question to chat or just raise your hand, and then I'll try to unmute you. I would have one question about the experiments. So why do you think actually the select the FedSparse, I think, was mid? It was like, I think, two slides before, was not reaching nearly the accuracy of, let's say, FedAvg.
Yeah.
For instance, this one. Like,
yeah.
Do you have any reason for that? Because what I would expect is if you just train the same sparse model on the whole data set, you shouldn't see that much of a accuracy drop.
Yeah, that's true. So if you take centralized training, let's say, and you try to learn a sparse model, then you don't really lose. I mean, you can compress and not really lose that much performance.
Yeah, and up to quite high sparsity, right?
Yeah. So my hypothesis is that probably non-IAD data tend to do that. We haven't really actually experimented on IAD data to be able to say for sure. But the FedSparse problem is a bit more involved optimization problem, especially due to the fact that we have this discrete case. And I didn't say here for how we actually do this optimization, but we sort of relax it to some kind of continuous optimization problem and then sort of revert back to the discrete version when we are to communicate it. So there are these sort of model choices we did, which might not be the best thing to do. So there's, I believe, sort of a combination of optimization and non-IAD data.
Yeah. So maybe do you think there is kind of methods that tries to do variance reduction in federated learning, some kind of for instance, scaffold that actually try to also learn the shift, so kind of the optimization looks a bit more IID could fix that?
Yeah, interestingly to say that. So we actually do have some experiments in the appendix where we did applied essentially scaffold on top of FedSparse, and it does seem to do better. That's for sure. But I mean, one of the problems of scaffold is that you have this kind of state on the clients, which, if you have let's say, a lot of clients in the case of MNIST, or if you scale up to something more, that you don't really know how stale these states are and whether they're still informative. So if the federation is small, that is something that would be helpful.
Yeah, so maybe with respect to that also, like, why do you think it's kind of like, because it seems that in this experiment, it's really like sparsity is what hurts the performance, because like FedAvg by itself also going to suffer because of non-IID data, but you don't see that accuracy drop, but you only see that in this FedSparse.
Yeah,
okay.
yeah.
So I was wondering, maybe like, do you see why is the sparsity problem here?
Yeah, I mean, it is a smaller model, so it could be, I mean, you do get a smaller model, and that smaller model might be more susceptible to non-IID data compared to the larger model that Federated averaging has. Yeah, unfortunately, I don't really have a very satisfying answer to that. Would be good for myself to also know the answer to that, so that we can sort of design around that. But yeah.
Thank you.
Yeah.
I don't see any other questions in the chat. Let me just double check, or there are no raised hands, so please just continue.
All right. So then for the second part, I'm going to talk about private and communication efficient federated learning. Sort of, we argued that communication and privacy are two important challenges at the beginning, and here are sort of some examples to demonstrate that. As I said, federated learning requires communication of large models between the server and the user, and the cumulative communication cost can actually be significantly larger than sending the data. And here I have some numbers to back it up. So we did one experiment on Stack Overflow, for example. The dataset size of itself is 14 gigabytes. And if you train a relatively simple logistic regression model on that for a specific number of rounds, and you measure the cumulative communication cost that was incurred for the entire training, you can see that that adds up to something along the lines of 3.3 terabyte, which is sort of much larger than actually sending the data set itself. And then, moving on to the privacy side, federated learning is not inherently private, even though we did not send the data over to the server. And that is because model updates can still reveal private information. For example, a sentence completion sort of algorithm can suggest endings based on someone's private information. And there have actually been successful attacks that show that you can perfectly reconstruct some sensitive user data in the federated setting just from the updates alone. And you can see one example here. All right, so this is now where epsilon delta differential privacy comes in, which is a way to provide strong privacy guarantees, and it's sort of widely adopted in the literature. So the idea is that we randomize the output of the algorithm such that the results look similar regardless of whether a specific data point or a specific user participated in generating that specific result. So more formally, assume that we have two data sets, D and D prime, where D prime is the same as D, except that we remove one specific user. Then the differential privacy, epsilon delta differential privacy, says that for any possible subset of outputs we can have, the probability of observing that specific subset when a user is included is upper bounded by the probability of observing that specific result when that user is removed, and how much is a function of the epsilon parameter. So essentially, the smaller the epsilon is, the more private we are, because the closer these two probabilities become. And we also have a plus delta, and essentially delta can be understood as the probability of failure. So the probability of that we cannot have a specific differential privacy guarantee, and delta is usually assumed to be something very small. All right. So how is epsilon delta differential privacy realized in machine learning and federated learning? So this is usually achieved by introducing randomness, either in the gradients or the updates. And one specific example is the Gaussian noise mechanism, where let's say we have phi, which is what we want to send, and then we essentially sample xi from some zero mean with a specific variance sigma squared Gaussian, and then phi tilde is the output, the randomized output of our mechanism. And differential privacy in the federated setting now has sort of two potential settings, the central differential privacy and the local differential privacy. In the central differential privacy, the server is sort of trusted and can see raw gradients and updates, and the noise, this Gaussian noise, for example, is actually at the server. And then there is the local differential privacy setting, where the gradients are randomized before actually being set from the device to the server, so the server can theoretically be untrusted. The second privacy setting is sort of much more stringent and usually leads to more loss of performance compared to the central DP. All right, so a way that I like to think of epsilon delta differential privacy is in terms of information. So if we want to bound essentially how private we are, bound the epsilon, what we could do is bound the amount of information that a user update or an update that involves a specific user contains relative to the information that is being sent when that user does not participate. For epsilon delta differential privacy, the notion we use to bound this information is the RENE divergence, which has a specific parameter lambda. And essentially what we want to do is bound the RENE divergence between these two distributions with some constant C that depends on the order lambda. And that C of lambda is the privacy cost for that specific order. All right, and now this brings us to DP-REC. So essentially what we can see is that the compression, doing some form of compression necessarily decreases the message size that we want to send, and as a result the message itself contains less information compared to the uncompressed variant. And furthermore, as we discussed in the previous slide, a differential private model update also contains less information about the delta. So theoretically, we could sort of combine these two arguments and design a differential private, or basically realize that the differential private model update needs less information. It potentially could be compressed for free. And that is how DP-REC arose, which we sort of designed in order to exploit this specific property. So we will show later that it can provide competitive accuracy and privacy guarantees, while also drastically reducing the communication costs. And you also prove that differential privacy is actually what enables high compression with this specific compression scheme of DP-REC. All right, so REC essentially stands for relative entropy coding, and this is a compression method proposed before in the literature, and works by assuming that there is some common information between the sender and the receiver, client and server, which is in terms of a distribution P. And there is also a shared random number generator. And what we want to do in this case is to compress a sample from Q. Q, you can think of it as the randomized mechanism that happens on the client, sort of the noise sample that the client wants to send. And how we do the compression is that we generate capital K points from the prior P. And then we select the index of a specific point from the available samples with probability that is proportional to the ratio between the local probability for that specific sample K and the prior probability for that, or shared P probability for that sample K. And then we just communicate the index K star and not the actual sample. And then if we want to reconstruct or decode, what we do is we use the shared prior P and the pseudo-random number generator, which is shared between the sender and the receiver, to generate the actual value for that specific index K star. All right, so how can we apply this idea to federated learning? So we saw that here. We call the algorithm FedREC. So we start with a client, we set the state of the pseudo RNZ to R, and then we form the message that we want to send. That would be the difference between the client-specific parameters and the server-specific parameters. Then we draw K samples from the prior, which is zero mean normal with a specific variance sigma squared. Again, this is known to both the server and the client. Then we form these importance weights where we evaluate the probability of the generated samples under both the Gaussian centered at the message that the client actually wants to send, and the zero mean Gaussian, which is the common information between the client and the server. And based on that, we basically select a specific sample, and we just return the index k star, which we can encode with log2k bits to the server. And then the server, given, just sets the state of the random number generator to R and generates samples from the shared prior up until it gets that specific k star sample. So intuitively, we can understand FedREC as doing vector quantization because essentially we can compute these sort of importance weights while considering multiple parameters at the same time. So therefore, we can encode the group of parameters to a single index, where now though the code book is sort of random because it is given by the samples that we generate from the shared prior. All right, so then how can we enforce differential privacy in this kind of algorithm? Actually, it is quite simple. What we do is we just clip the update norms to have a specific L2 norm of C, which is also how you usually do it when you do differential private federated averaging. And this suffices to show that this overall algorithm is differentially private. And here we sort of show the formal differential privacy guarantees. So we can basically show that we have a cost that is equivalent to sort of the standard Gaussian mechanism, which we see here. However, the privacy cost of each iteration is sort of roughly two times what you would observe if you didn't do the DP recompression and just use differential private federated averaging. So that is a bit unfortunate. And we also have this important sampling overhead, which we essentially add to the delta. That's because we only draw k samples from the prior, so we have to properly take into account that we have a finite sample to estimate the privacy cost. And that overhead scales with respect to the Rényi divergence of order 2, essentially. But it quickly decays with the bitrate B. So the larger the bitrate, the more this important sampling overhead is not really significant. All right. And yeah, basically that's the overall method. And then going on to the evaluation, we had 4 tasks: MNIST, FEMNIST, where we used the LeNet 5 model; Shakespeare, where we used an LSTM model; and the Stack Overflow task I described in the beginning, where we used the logistic regression model. For baselines, we have differential private federated averaging, provides central DP guarantees, has no compression. We also had a DD Gauss, which is something that a method that can provide central DP guarantees while also quantizing essentially its parameter to from 12 up to 16 bits. Sort of serves as a method that can also reduce the communication costs. And then we also have DP-REC, where for the client to server communication, we essentially encode its tensor of parameters, so the parameters for a specific layer, to a single 7-bit integer, which corresponds to the possible indices or samples we can have from the prior. And for the server to client communication, we can also do some compression there. And this is primarily because we have so much compression from the client to server that it actually becomes cheaper to communicate the actual compressed gradients to the clients, and then the clients can sort of reconstruct their old version of the global model to the new one instead of just sending directly the global model. And we also provide central DP guarantees. So for evaluation criteria, we want to, of course, measure accuracy, also how much we can compress, and also at what kind of differential privacy or privacy guarantee we have. Each of these sort of criteria sort of affects or is correlated with the others. All right, so I mentioned in the beginning that there is some interplay between privacy and compression, and this here is something to illustrate it. So consider that we want to communicate an epsilon delta differential privacy, differential private methods. What we can show is that with DPREC, a sufficient bitrate is on the order of epsilon, where epsilon is the primary parameter that denotes how private we are, plus some logarithmic term, which depends on the delta that we assume and also the target compression error. And this bound is sort of similar to bound that have appeared in previous works and also concurrent works with ours. Sort of as a corollary, we now have that the DP constraints directly affect the compression rate of the relative entropy coding scheme, because for meaningful privacy, epsilon is less than 10. So therefore, the messages can be highly compressible. And this is something we saw here, where with the bright yellow, is basically communicating an epsilon delta or training with epsilon delta for a specific epsilon delta guarantee without doing any compression when we communicate the samples. And we have 8 tensors with a total of 225,000 parameters. And here, the other sort of lines are what happens when we do the DPREC compression, where we only return essentially 8 integers from the client to the server. And each integer can have 4, 5, 6, or 7 bits of resolution. And we see that if we go up to 7 bits, the performance is practically the same as the no compression baseline. So we can actually do this substantial amount of compression. All right. And now showing the results on the tasks I described before. So it should be noted that the x-axis, due to the amount of compression we do, is on a logarithmic scale. Sort of we can see that assuming that we get essentially an accuracy level that both DPREC and the differential private federated averaging can reach, we can get, on MNIST we have extreme amount of compression, 1700x, whereas on FEMNIST we have something more moderate, 8.4x, but we also lose a little bit in terms of the privacy guarantee, going from 3.6 to 6 and from 3.7 to 5.7. And this is primarily due to the bound we saw before, where roughly require twice the privacy cost for per iteration compared to differential private federated averaging. All right, and then on the other 2 tasks, the Shakespeare and the stack overflow, again, if we target an accuracy that both methods can reach, we can get a significant compression, again with some loss in privacy. And yeah, for Stack Overflow, since the dataset is so large, the evaluation, we do the full evaluation only at the end of training. So what we plot here is just the evaluation on random subset. So essentially, we only measure the compression ratio at the compression rate at just the end of training. Yeah, and here are the table that has the actual numbers. So generally, we can see that DPREC does have lower accuracy compared to differential private federated averaging. And this is primarily because differential DP federated averaging goes directly for a central DP guarantee, whereas with DPREC, we sort of go from a local DP guarantee to a central DP guarantee by just using privacy amplification due to the fact that you select a random subset of clients, which is sort of weaker. So therefore, we have to clip more aggressively to maintain the specific privacy guarantee. If we compare against the TT Gauss sort of method, can also save communication costs, we see that if we pick the aggressive TT Gauss setting, where you only have 12 bits per parameter, we actually have either much better performance on sort of low or high privacy settings, or a bit worse performance if you go to the low privacy settings, but we have much more compression compared to TT Gauss. And that is something we can also see here, where now also the gap between the differential private federated averaging and DPREC is much smaller, and that is because we have quite a lot of clients in this specific setting. So therefore, we get quite a lot of privacy amplification in our case by sampling a random subset. So therefore, we can clip less aggressively. And we see that we can reduce the previous 3.3 terabyte I described in the beginning to just 32 gigabytes. All right. Yeah, and that's basically it. Conclude here. So we introduced a unified approach to essentially having private and compression efficiency in federated learning using differential privacy and relative entropy coding. We showed how DPREC can achieve state-of-the-art privacy guarantees. We can achieve an epsilon of 6, 3, and 1, while also getting up to 3 orders of magnitude compression ratio. And we do suffer a little bit on the accuracy side, but can be depending on the size of the federation within a few % of the private non-compressed solution. And as a main directions for future work, we would like to integrate DPREC with some sort of secure aggregation or shuffling in order to get more privacy amplification and bring it more in line with the accuracy numbers we get when we do standard differential private federated averaging. Yeah, and that's it. Thank you very much. And yeah, if you have any questions about this part or the first part, yeah, feel free to ask.
Thank you, Christos, for your great talk. So please, if you have any questions, just raise your hand or just post your question to the chat. I would start with one. So for DPREC, you showed this privacy guarantees. I was wondering also, like, can you also argue what happens with the convergence of the actual, like, when you employ DPREC with FedAvg? How does it affect the theoretical convergence of the method? Yeah,
that's an interesting question and something that we are exploring. So intuitively, I would say, due to the fact that the bias essentially we have by doing the importance sampling approximation is relatively small due to the fact, I mean, empirically, we also see here that if we do this extreme compression, we don't really lose much compared to not doing any compression at all. And you can also see it from here that if we want to have a good privacy, we have to reduce the importance sampling overhead as much as possible. So we'd not introduce too much error by doing this compression. So assuming that there is, I think there are some works that show that standard differential private federated averaging can converge with a specific rate. I would not expect, I mean, this would probably converge a bit slower due to the fact that this error is not 0. But I would not expect it to behave, vastly different.
So if I understand correctly, the compression that you do is unbiased, right? Because you do the sampling based on
the compression is biased. So the thing is, because we have k samples, so we have a finite number of samples. So theoretically, if we could have an infinite number of samples, then the compression would be unbiased. But due to the fact we have a finite set, the compression is biased. But that bias is sort of essentially controlled by this term here. So therefore, the closer we bring the update distribution to the server distribution, so to speak, then the smaller that bias becomes. But it is still non-zero.
Thank you. So maybe one more question, more like general question. So about federated learning and production. So what would be the technologies and algorithms that you at Qualcomm would use to actually ship some FL algorithm? So what do you think that are the technologies that are already like mature enough that you could use them in production?
Yeah, I mean, the standard federated averaging algorithm, that's something we actually have a demo that you can find online on YouTube, where we have, for example, a specific use case of user verification. Let's say you talk to your phone and the phone needs to understand that it is you. And that underlying model is trained using federated learning. So in terms of technology, this requires you to have some form of engine to train on device. Ideally you'd like to do this on the GPU, and of course also communication efficiency is important for this kind of settings, especially if you want to move to some kind of, let's say, always on solution where you communicate while being on mobile data, not just Wi-Fi, and you can train while being on battery and not really plugged in, right? So all of the challenges I described in the beginning are sort of important challenges for the practical applications.
Thank you. So let's see how we're exactly on time, but maybe we have still time for 1 or 2 more questions or comments. Please do not hesitate to either raise your hand or just post your question. Okay, so it seems there are no further questions. With that, thank you, Christos, again for your excellent talk.
Thank you for inviting me.
Pleasure to have you. One last thing that I would like you to ask, just send me your slides also. I would like to post them along the video recording.
Will do. Okay.
Yeah, and thanks everybody for showing up today, and hope to see you all next week. Thank you again, and have a nice rest of the day.
Thank you. You too.